Studying the difference between linear and exponential growth is important because it helps us understand how various phenomena change over time. Linear growth is steady and constant, while exponential growth can accelerate rapidly. Recognizing these patterns is vital in fields like economics, biology, technology, and help guide our decisions and help us make predictions in areas ranging from population growth to investment strategies. Let's start by taking a look at an investment that demonstrates linear growth. The investment starts with $500 and increases by $60 each year. So starting with $500 and adding $60 every year for 12 years, we end up with $1,220. Notice that with linear growth, we're adding the same amount each time. In this case, we are adding 60. So the rate of change is 60. Let's look at a different investment where we start with $300, but this time our investment grows by 13% each year. Right, to figure out how much that is, we're going to take our original $300 and add 13% of 300, which would be 0.13 times 300. So it's what we started with plus 13% of 300. So that would be $339. So notice it increased by $39. Now we have $339. So to figure out how much we have after the second year, we would do 339 plus 13% of that. And notice we're doing 13% of a larger number this time. And when we work that out, we get $383.07. And this time it increased by $44.07. So it increased by more. Now there's a shorter way to calculate this. Instead of taking the number and then adding 13% of that number, we can just take the number and multiply by 1.13. So the 1, that represents what we started with, and then the 0.13, that represents the 13% we're adding. So it's like taking 113% of what we started with. So now I'm going to fill out this table, and I'm going to be multiplying by 1.13 each time. So after 12 years, our $300 investment grew to $1,300.36 by growing 13% each year. Now notice we were repeatedly multiplying by 1.13. And since that number is larger than 1, it kept making the number larger. And the 13% increase was larger and larger every year. By the time we got to the 12th year, it increased by $149.60 just in that 1 year. So we started off by adding $39 from year 0 to year 1, but from year 11 to year 12, we ended up adding $149.60. So the rate of change for this investment was increasing. as we added more and more each year. Now, thinking back to the linear growth, we were repeatedly adding the same number each time. But in exponential growth, we're multiplying by the same number each time. The reason we filled this chart out to 12 years, because that was the first year where account B had more money in it in the end. If we go back to the linear growth investment, account A started with more money in it, but after 12 years, that was the first year where it had less money than account B. And as this investment continues, this rate of change is going to keep increasing by more and more as we multiply by 1.13. So in year 12, account B catches up and passes account A. Okay, let's read through this scenario and classify it as linear or exponential. Sophie received a golden barrel cactus. After 1 year of caring for it, it grew from 6 centimeters to 7 centimeters. After the second year, the golden barrel cactus was 8 centimeters tall. After 3 years, Sophie's golden barrel cactus had grown to 9 centimeters tall. Well, we notice here that we're adding the same number each time. So we have a constant rate of change. So this will be a linear function. Here we have another scenario. Let's classify this one as linear or exponential. A bacterial culture starts with 80 bacteria at 8 a.m. At 9 a.m., there are 240 bacteria. By 10 a.m., the culture has 720 bacteria. At 11 a.m., the culture has grown to 2,160 bacteria. So in this case, we are multiplying by 3 each time. So since we are repeatedly multiplying by the same number, this is an exponential function. Let's classify these equations. Now here we have an equation in slope-intercept form. So we have a slope of -9 and a y-intercept of 6. And equations written in slope-intercept form make lines. And lines have a constant rate of change. So in this particular line, as x increases by 1, the y's are going to decrease by -9 each time. So this is a linear function. It makes a line, it has a constant rate of change, and the y's keep decreasing in this case by the same amount each time. Now here we have an equation where x is in the exponents. And equations where we have x in the exponents, those are exponential functions. Let's take a look at one more comparison of these two equations. The linear function would have a beginning point of 0, and we would subtract 9 each time. So here the rate of change is -9. It's a constant rate of change. Now here the beginning point will be 7. And as x increases, we keep multiplying by another 2. So when x is 1, well, we multiply by 2, so it's doubled. Well, then we multiply by 2 again, so now we're doubling 14. So instead of going up by 7, we went up by 14. Then we multiply by 2 again, and that would double the 28. And notice that when we multiplied by 2, we added 28. So if we look at the rate of change, we added 7, we added 14, we added 28. So we keep adding more and more each time. Okay, let's take a look at one more comparison between linear and exponential growth. Sherry sells 60 ice cream cones after 1 week. Each subsequent week, she sells 45 more ice cream cones. She starts by selling 60, Then each week she sells 45 more. So she starts with 60, adds 45, adds 45 again, adds 45 again, and so on. So each week she's selling 45 more ice cream cones. Now Aaron, he sells 30 ice cream cones after 1 week. So notice he starts with fewer ice cream cones than Sherry. Each subsequent week, Aaron sells 5% more than the previous week. So he starts with 30, and then he sells 5% more. Well, 5% of 30, that'd be 0.05 times 30. That's only 1.5 more ice cream cones. So that would be 31.5. But then the next week, he's selling 5% more than 31.5. So now he's adding a little bit more than 1.5 ice cream cones. So that week he sells 33.075 ice cream cones. We are multiplying by 1.05. The 1, that includes the amount from the previous week, and we're adding 5% more. So we're finding 105% of 30, and then we find 105% of 31.5. Okay, now Aaron's totals don't look very impressive here compared to Sherry. But remember, Sherry always sells 45 more ice cream cones than the previous week. So she has a constant rate of change. But Aaron's pattern demonstrates exponential growth. So if they continue forever, since Aaron is selling more and more and more each week, eventually Aaron will be selling more than Sherry. His rate of change is increasing. So eventually he will catch up to Sherry. So given this scenario above, if each salesperson continues the pace forever, who will sell more ice cream cones? Aaron. Because his pattern demonstrates exponential growth. At first, his ice cream totals are growing slower, but over time, he will catch up to Sherry. I hope these examples about linear versus exponential growth have been helpful. This is Mr. Ela, signing off.